going to talk about continuity. So a function is continuous over an interval, which is just a part of the graph, part or piece of the graph. If its graph over the interval can be drawn without removing a pen from the paper. A function whose graph is broken, disconnected at x equal to c, is said to be discontinuous. So the only reason why a graph would be broken is if it has a vertical asymptote or if it has a hole or an open circle. Or if it's a piecewise function. With pieces separate from each other. With separate pieces. So the definition of continuity. A function, so this is just the general term, and then unfortunately the calculus might confuse it, but here it is. Definition of continuity: a function f is continuous at a point x equal to c if the limit of the function as x approaches to c, it exists. F of c, which is the y value at x equal to c, exists. So that means that it's a closed circle. And the limit of the function as x approaches to c is in fact f of c, which is the closed circle. So a function is continuous on the open interval ab. If it's continuous at each point on the interval, we could have a one-sided continuity, aka continuous on the left or the right. We could also have it on a closed interval or a half-closed interval. So we could just be looking at a piece of a graph. So let me write that down. A part of a graph can be continuous even though the entire part might be discontinuous. Entire graph is discontinuous. So for example, if I'm looking at this graph right here, the entire graph itself is discontinuous because there's two pieces. I have to lift up my pen in order to complete the entire graph. However, if I'm just looking at this piece from here to here, that one is continuous. So that's what that paragraph says. Okay, so this theorem, again, with the calculator, we can see if it's continuous or not. With the graphing calculator, should be more specific. But just listed here, a constant function f of x is equal to k, where k is a constant. It's technically just any line y equal to whatever line. So if it's a horizontal line, and for sure it's going to be continuous. For b, any positive integer f of x equal to x to the n is going to be continuous. So for b, if I have an x squared or an x to the fourth or an x to the sixth, so on, it's going to end up looking like this. So it's definitely going to be continuous. If I have an x to the third, x to the fifth, so on and so forth, it's going to look like this. And that one is also continuous itself. Technically for part C, it's the same thing as B, except that we just have n behavior. So x to the any even power is going to have, sorry for my dogs, n behavior like this. Or if it has a negative, it'll be upside down. Sorry for that. And x to the odd power. And same thing with these. If it's a negative, this will be upside down and this will be reversed. So x to the odd. So B and C are technically saying the same thing. So if it's a high power, I should just do this right here. Sorry about that. And if it has a negative in front of it, something's going on in the middle like this. For D, any rational function is continuous except for all the x values that make the denominator 0. So there's a bunch of examples, but for example, if I have 1 over x, well, we know we can't divide by 0. So we know that we're going to have, at the origin, we're going to have technically a vertical asymptote. And the graph is going to look, so there's the vertical asymptote. And the graph looks something like this. And so where is it going to be continuous? Only in this piece or in this piece. But together, it definitely isn't continuous. For E, n is an odd positive integer greater than 1. So n is going to be your root. So it has to be 2 or more. It's going to be continuous wherever f of x is continuous. So for part E, just as an example, if I have the fifth root of x squared, well, the fifth root of, you can take the fifth root of any number, except that x squared is going to be, x squared is continuous based on part B. Right here, it's going to look like this. So since x squared is continuous, then the fifth root of x squared is continuous all throughout. And again, we can graph it. Now, f has a weird situation. So n, which is the root, it has to be an even positive integer. So we've learned that for square roots, we can only take the square roots of positive numbers, because if we want to take the square root of negative numbers, they're imaginary. You have that letter I there. So the only issue here is that for even positive roots, it's going to be continuous wherever f of x is continuous, so just as the same condition as before. However, it has to be non-negative, which means that it has to be greater than or equal to 0. So for example, if I have the square root of x, well, x has to be greater than or equal to 0. This is where it's going to be continuous. It's not even going to exist for negative numbers. Okay. So we're going to solve inequalities using a sign chart. And we have some steps there. And I should have cut this off, but before I actually go over these steps, I apologize. These instructions should have been here. So we're going to determine first where each function is continuous before we do this sign chart. So we have h of x is equal to 4 minus 2x. All right. So I'll leave it up to you to graph it, but this right here, the highest power is a 1, so this is a line. And my slope is -2, and my y-intercept is 4. The important thing, again, to notice that it's a line. So if it's a line, it's continuous all throughout. So line, therefore, it's continuous from -infinity to +infinity. We can also say that it's going to be continuous for x being an element of all the real numbers. These two things say the same thing, one in interval notation and one in set builder notation. All right, so for the next one, again, we can graph it, but this is a rational function. It's 2x divided by x minus 4, we know that we have a problem at x equal to 4 because of the denominator. So an x value, it can't equal to 4 because 4 minus 4 is 0 and we can't divide by 0. So we know that there's a vertical asymptote at x equal to 4 because there's not a factor of x minus 4 on the numerator that we can simplify it out to make it an open circle. But we know there's a vertical asymptote, and again, you can graph it. And so here, we're going to say vertical asymptote at x equal to 4. Therefore, it's going to be continuous in two separate pieces. It's going to be continuous from negative infinity to 4, and then a little u for the second piece, and then from 4 to infinity. Or we can just say that x can equal to 4, and it can equal to any other number. So again, this part right here and this say the same thing. The last one, k of x is equal to x minus 2 over x squared minus 2x minus 3. We can graph it, but again, we might run the risk if we miss any open circles. But let's see. So I'm going to factor this one out. So this is going to be x minus 3 times x plus 1. So if we notice the factors are not the same, so technically we don't have any open circles, we know that we have, so I should say that the factors are not the same in the numerator and the denominator. We can simplify it out. So we know that we have vertical asymptotes at x equal to 3 and x equal to negative 1. So for continuity, it's going to be continuous from negative infinity to negative 1, and then from negative 1 to 3, and then from 3 to infinity. Now this one I will graph so we can confirm. So I'm looking at this one, and I had already graphed it right here. And so I'll do a quick little sketch so that I can mark it up here. So I have a graph at negative 1 here. I have a vertical asymptote. And it looks something like this. And then at 3, I have another vertical asymptote. And it's looking something like this. And then it looks something like this. Okay. So let's match the pieces. So it's continuous from negative infinity to negative 1. This one right here is for this piece. And then from negative 1 to 3, this piece is for this piece. And then it's continuous from 3 to infinity. This piece is this piece right there. So again, you can use the theorems that are up at the top or just your graphing utility. All right, so solving inequalities using continuity properties, which using a sign chart. So I'm right here. So theorem 2 says sign properties on an interval AB. So again, this interval AB is just a piece of the graph, part or piece of the graph. So if the function f is continuous on an interval AB and f of x can't be equal to 0 for all x and a in the interval AB, then either f of x is greater than 0, which means that it is positive, or f of x is less than 0, which means that it is negative. So it's very important to understand that. A real number, a real number x is a partition number or a critical number for a function for all x and f if for all x and f is real at x, or for all x and f of x is going to be equal to 0. So partition numbers determine the open intervals on which f does not change the sign. So it'll be much easier to understand once we do a problem here. So we have some steps. It says constructing sign charts. So given a function, it says find all the partition numbers of f. So how are we going to do that? We need to find where it's discontinuous, which means we're going to make the denominator equal to 0 and find all the x values for that. And we're going to find all the numbers that make the function itself equal to 0. So we find where the numerator is 0 and the denominator is not 0. Step 2, we're going to plot the numbers found in step 1 on a real number line, dividing it into intervals. And then we're going to select a test number in each open interval and see if it's positive or negative. And we're going to finish the sign chart using what signs, positive or negative, that we found. So let's do this problem, right? We have 2 of them. So it says, use a sign chart to solve each inequality. Express answers in inequality and interval notation. Okay, so we have x squared plus 2x minus 8 is less than 0. We need to walk out understanding that this is technically a parabola. And then this is technically the line y equal to 0, which is the x-axis. The y-axis, excuse me. Sorry. And we want to know for less than, we want to know when the parabola is below the x-axis. That's what that mathematical statement is saying. We want to know when that parabola is below the x-axis. Not on it, not above it, but below it. So I'm going to graph it. I'm going to actually get the answer before we do all this process, that we appreciate and understand graphically what's going on. So I have, and I did not put it in. So I need to type it in. X squared plus 2x minus 8. So there's the parabola. And I want to know when it's below the x-axis, because y equal to 0 is the x-axis. So I'm really interested in those points. So right there, the parabola is on the x-axis. So to just show that it's below, I'm going to put those 2 open circles, those 2 coordinates, as open circles. So I'm going to go ahead and graph it right here. So it's a right side up parabola. It's not going to be to scale. But I'm just interested from here to here. And this is going to be -4. And this is going to be +2. So it's definitely not to scale. So when is it going to be below? So now that I just graphed it, my answer is technically from that open circle, all the answers here, all the way to that open circle. So my answer, when is this parabola below the x-axis? It's from parentheses -4 all the way to 2 in interval notation. That's my answer. That's my answer. In set builder notation, it would be x is less than 2, and it has to be greater than -4. So now we're going to do these steps. Okay, so going back to your steps, step 1a says find all numbers x such that f of x is discontinuous at x, which means just set the denominator equal to 0. So step 1a, I'm going to put it right here in blue. So step 1a is not applicable. Not applicable. We don't have a denominator. All right. Sorry. Step 1b is technically to find the set the numerator equal to 0. Well, I really could have x squared plus 2x minus 8 over an understood 1. So my numerator is going to be x squared plus 2x minus 8. And I'm going to set it equal to 0. So this is a parabola. It's set equal to 0. You can solve it by completing the square, by factoring, by using the quadratic formula. Well, this is factorable. So it's going to be plus 4 and a minus 2. So if you look back at the notes, so step 1b says, find all numbers x such that f of x is equal to 0. So here, we're going to set each factor equal to 0 to find them. So I'm going to write that in a different color. Set each factor equal to 0. So I'm going to have x plus 4 is equal to 0 and x minus 2 is equal to 0, and I'm going to solve for x. So I'm going to have x equal to -4 and x is equal to +2. So that's step 1. Step 2 says plot the numbers found in step 1 on a real number line. Okay, so here we go. So here, where am I going to plot it? I'm going to do it right here. For step 2, I'm going to plot it. And this is what we found so far. So here's -4, and here is 2. And what we found so far is that the function, I'm going to call it right here, f of x, we know that it is equal to, at -4, we know that it's equal to 0. Because technically, it's this point right here. And at 2, it's also equal to 0. Which is this point. It's the y value for this point right there. So that's step 2. Step 3 says select a test number in each open interval. So you need to realize that we have 1, 2, 3 open intervals. We have 3 open intervals here. So interval number 1 goes from -infinity to -4. Interval number 2 goes from -4 to 2. And interval number 3, so I is for interval, is going to go from 2 to infinity. So step number 3 says to pick a number for each interval. So here I go. So for step 3, for interval number 1, you need to pick a number in between -infinity and -4. On a good day, you could pick -5, -10, whatever you want. On a bad day, pick a number that's to the right of that. So I'm going to put here that we pick, -5. And what we need to do is we need to insert it into the function. So we're going to do f of negative 5. So the function is x squared. So I'm going to put negative 5 squared plus 2 times negative 5 minus 8. So negative 5 squared is 25 plus a negative 10 is 15 minus an 8 is 7. But really, what we're only concerned with is the fact that it is a positive number. So right here, I'm going to put that for any number that you pick, your f of x is going to be a positive number. So for interval number 2, I'm going to say that we pick any number between negative 4 and 2. Well, I'm going to pick 0. And I'm going to go back and substitute it into f of 0. F of 0 is equal to 0 squared plus 2 times 0 minus 8 is going to give me negative 8. But again, I'm concerned with the fact that it's a negative number. So that negative means that for any number that you pick in this interval, it's going to be negative. And for interval number 3, it has to be a number between 2 and infinity. Well, I'm going to pick 3. So we pick 3. So f of 3 is going to be, 3 squared plus 2 times 3 minus 8. So 3 squared is 9 plus 2 times 3 is 6, is 15 minus 8 is a positive 7. And again, we're just concerned with the fact that it is positive. Okay, so that was step 3. So step 4 is to construct the sign chart. Well, we actually already did. It's in step 2. And if you notice, so I'm going to have to zoom out here. So for below, for step 4, let me go in here. So I'm going to add this for step 4. For step 4, this below, which means less than 0, means that we're looking for negative answers. Therefore, our only answer, I'm going to highlight it here in pink. This is the negative that we're looking for. And so our answer is this interval right here. And it's the same answer that we got looking at the graph. The two positive ones are technically the part of the parabola that are above the x-axis that we were not interested in when we graphed it. Okay, so now let's try the second one. So x minus 4 divided by x squared plus 2x is greater than 0. So if you are going to graph it, make sure that you understand that this is going to be some rational function. What's happening? Sorry. So this is going to be a rational function. And this part is that you want it to be above the x-axis. So for our part, for the signs, above the x-axis means that we're looking for positive answers. Okay, so let's do these steps here. Okay, so let me divide this out. All right, so step 1a. We need to set the denominator equal to 0. So it's x squared plus 2x is equal to 0. It's a quadratic. You can solve it by factoring, by completing the square, using the quadratic formula. This is factorable. They both have an x. So it's going to be x plus 2 times x plus 2. And we set each factor equal to 0. And we solve for x. So we have that one and we have that one. For 1a anyway. For 1b, we set the numerator equal to 0. And we solve for x. So what we know from 1a is that at x equal to 0 and x equal to negative 2, we have a break in the graph. And it's going to be vertical asymptotes because there's no factor that's the same in the numerator. Again, you can graph it. And we also know that at x equal to 4, the numerator is going to be 0, so my answer is going to be 0 for that fraction. Okay, so let's put that in step 2, what I just said. So in step 2, we're going to do the number line. And we got to put these in order. I apologize, there should be a 4. And they don't have to be to scale. So just negative 2, 0, and 4. And so what we know so far is that the function f of x at 0, it does not exist. And it does not exist either at negative 2. Why? Because we set the denominator equal to 0, and we said, well, those x values are going to make my denominator 0, and I can't divide by 0, so I know it does not exist. Again, either it's going to be a vertical asymptote or a hole. In this case, it's a vertical asymptote for both of them. And at x equal to 4, we know that your y value is going to be equal to 0. Okay, so we cut our piece of the number line into 4 intervals. So we have interval number 1, interval number 2, interval number 3, and interval number 4. And so we need to pick so for 4 different numbers, 1 for each interval. So for interval number 1, let's say we pick negative 3. And you would substitute it in or put it in your calculator. It would be negative 3 minus 4 over negative 3 squared plus 2 times 3. Negative 3, excuse me. So you get that, and you're going to get negative 7/3. Again, we're interested in the fact that it's negative. So this one is negative. For interval number 2, let's say we pick, it has to be a number between negative 2 and 0. So we pick negative 1. And once you do the whole substitution, you should get 5 over 1, which makes it a positive number. So this one is positive. So you're going to get positive numbers in that interval. For interval number 3, so it has to be a number between 0 and 4. So let's say we pick 1. And after you do the whole substitution, you get negative 1. So again, makes it negative. And the last one, interval number 4, let's say we pick, so it has to be a number greater than 4. So let's say we pick 5. And after you do that whole substitution, you're going to get 1 over 35, which again, we're just concerned with the fact that it is positive. So without graphing, we are interested, just as a reminder, we're interested in positive answers. So this one's positive and this one's positive. So that means that this interval and this interval are our answers. So let me write them down. So our answer is going to be, in interval notation, it's going to be from negative 2 to 0, little u, and 4 to infinity. In set builder notation, we would say that x is less than 0 or greater than negative 2, or x is greater than 4. So there's that answer, and there's that answer. And you can check it with your graphing calculator. Okay. So it says use theorem 1 to determine where each function is continuous, express the answer in interval notation. So here we're going to graph them. So this is the square root of x minus 6. And so that's an important point to graph. So 6, 0. So this one looks, this is 6. It looks like this. So let me go back here and zoom in. So where is it continuous? It's going to be from bracket 6 all the way to infinity. So what theorem 1 says is this is a square root function. So it's an even root. Therefore, whatever's inside x minus 6, which is x minus 6, has to be greater than or equal to 0. So I'm going to add 6 to both sides, and x has to be greater than or equal to 6, which is the exact same thing as that right there. The next one, cube root of x minus 8. So cube root of x minus 8 is this one right here. So this is the cube root of x minus 8. So I'm zooming. I want to see if there's any break. No, there isn't. It's going on forever to the left, and it's going forever to the right. So let me do a quick little sketch. And that point, I guess, is important. 8, 0, and 0, negative 2. So it's not going to be to scale. But this one is 8, 0, and this one is 0, negative 2. So it's always continuous. So my answer is going to be from negative infinity to positive infinity. Or I can say that x is just an element of all the real numbers. So it's like a weird r. What does theorem 1 say? So you can take the cube root of any number, as long as you have to look at whatever's inside. And since, so the cube root of, you can take the cube root of any number, and x minus 8 is a line, which is continuous. Therefore, technically, this is our answer without using the graphing calculator. And the last one, cube root of 1 over x, excuse me. So you can, again, now doing the theorem, you can take the cube root of any number and 1 minus x is a rational function. So x cannot be 0 because we can't divide by 0. So technically here, in set builder notation, x can't be 0. And it's going to be continuous from negative infinity to 0. In parentheses, not brackets, and then from 0 to infinity. So this is the answer, or this one. This is the answer, or this one. And for this one, this is the answer, or this one.